In this video, let's talk about the cost function of a logistic regression. Now, logistic regression is a combination of a linear equation as well as a sigmoid function. So we already seen the cost function for a linear regression, which is j theta 1 is equal to 1 by 2m summation of I is equal to 1 to m h theta of xi minus yi whole square, right? Now we have learned about this cost function in linear regression. Now the cost function represents optimization objective here, right? Now we create this cost function and we'll try to minimize it so that we can develop an accurate model with a minimum error. Now this is my cost function for a linear regression. Now what actually I have is I also have a sigmoid function right here. Now I can directly use h theta of x here, saying that h theta of xi is equal to 1 by 1 plus e to the power of minus theta 1 into xi. Now what I'm trying to do here is I'm assuming that line is passing through 0 so that my intercept theta naught is equal to 0. That's why I just got theta 1 into xi here. Now what I'm trying to do here is I'm trying to substitute this equation here into this linear regression cost function. Now let me write that 1 by 2m I is equal to 1 to m 1 by 1 plus e to the power of minus theta 1 into xi minus yi whole square. Now can we use this equation? Actually we cannot use this equation. We have a problem here. We cannot use this cost function for a logistic regression because because in gradient descent, right? Suppose suppose if we have a gradient descent like this. Let me take another sketch. A gradient descent. Our gradient descent graph will look something like this in this case. Let's say we have here a j of theta 1 and here it is our value theta 1, right? This is our cost function and this is our slope. Now in the gradient descent problem, this equation creates a non-convex function here. Our graph will look something like this, which is a non-convex function, right? Which is non-convex function. Now what is actually happening? What is the problem here? See, we have lot of local minimas here. We can, in this problem statement, we can reach at any time with only a local minimum, which may give a wrong prediction. So we will never reach a global minima point here. So by using this equation, we'll definitely have a problem here. Now we just need a convex function. We just need a convex function like this, like we had in our linear regression, right? Let's say this is our j theta 1 and this is our theta 1, and we just need we just need a graph something like this which will have global minima. So this global minima we can achieve by using the equation here. Let me just write that equation. So that is called as logistic regression cost function. That means let me just take another sketch here. J of theta 1 is equal to see, we have two outputs here, like, okay, one is when y is equal to 1 and the other one is when y is equal to 0. Now here when y is equal to 1, we are using a logarithmic function and putting h theta of xi into it. Now here h theta of xi is nothing but our sigmoid function, 1 by 1 plus e to the power of minus theta 1 into x. So this is the equation, this is the cost function when we have y is equal to 1. Okay, now we have another equation when y is equal to 0. Now here also we are using a logarithmics, and here I wanted to write an equation h theta of xi. So this h theta of xi again is this. Now we have got two equations because this is a discrete output when y is equal to 1 and when y is equal to 0. Now based on these two equations, I can just draw a graph. My gradient descent graph will look something like this. Let me, not gradient descent graph, but a simply when I just draw the logistic regression graph, right, with respect to my cost function j theta 1, and with respect to my hypothesis h theta of x, let's say this is a 0 and we have 0 to 1, right? Now when y is equal to 1, according to this equation, our graph looks sorry, something like this. And this is how my graph looks like. It is not looking good actually. One second. It looks something like this. Now when my equation is y equal to 0, then my graph looks something like this. Now I'm trying to draw a graph between j theta 1 and h theta of x. Now here also I have a value from 0 to 1 because it is a classification problem. Now this time my graph looks something like this, and this is the curve when y is equal to 1, and this is the curve when y is equal to 0. Now by combining these two equations, right, now by combining these two equations, we can write a single function like this. How we can write? We can just write here, we can just write cost function of h theta of x comma y is equal to minus y into log of h theta of xi minus 1 minus y into log of 1 minus h theta of x. Right, now I can write this equation by combining the above two conditions. When if you apply if you put y is equal to 0 in this equation, you will get this equation, and you put y is equal to 1 in this equation, you will get this equation. Okay, now this is how my cost function looks like, right? Now what I'm trying to do here is I'm trying to apply a gradient descent algorithm for this equation. Okay, now the question arises, how do we reduce this cost value, right? Now that's why we are using this gradient descent. Now the main goal of gradient descent is to minimize the cost value. That means it minimizes the cost function. Now we have already seen that, right? Like the gradient descent equation, which is having theta j will keep on update its value theta j with the learning rate into partial derivative of theta j of here. I just wanted to say this cost function j theta 1, j theta j of theta 1. Let me just write here, guys. Now what I wanted to do here is I wanted to apply the convergence here. I wanted to repeat I wanted to repeat this until convergence. I wanted to repeat until convergence, because I just wanted to update this theta j until convergence. Repeat until convergence. Until convergence. Okay. So this is about the cost function and gradient descent of logistic regression. In the next video, we'll talk about the performance matrix of a classification problem. All right, we'll see you in the next video.